Okay, so the last bit of 5.3 that we were doing was solving for x in logarithm equations. So where we were was something like this. If we have log base 2 of 6x minus 7 equals 2. So we have a couple ways we could do this. What's one way? Any ideas? I'm sorry? Make what a base? The 2 on the right? How? Not sure where you're going with that.
Well, isn't it log base 2? Can we do that?
Log base 2. This 2?
Can we make that a base?
You can't make it a base because it's just a number. If you put a log on it, you're putting a log base something on it already. Yeah. So if it's a number, you can't make it change what it is, kind of thing. It has to stay as a number, kind of thing. So the first way, we have a logarithm. How could we change this into an exponential function? Base to the, which one? This side or that side? This side. So base to the answer equals the inside, right? So that's one way. So base to the answer equals the inside. That's one way. Or we could say, oh, that log has base 2. Let's put the log in the exponent of 2 on both sides, kind of thing. So 2 raised to this side of log base 2 of 6x minus 7 equals, now you have to raise the other side into the power of 2 as well. So we put this whole side in the exponent of 2, so that side goes into the power of 2. Right? We're doing that because these two are inverses. So they cancel, and we're left with just 6x minus 7 equals 2 squared, which is exactly this. Okay? So if you don't see this or you don't remember how to set it up, how to convert from log to exponent, then just use the inverse way. Okay? You get there, the same place, it just takes an extra step. Okay? So let's continue from here. What should we do next? Don't everyone talk at once. I told you I'm in a rare mood today. So, what about this side? How can we simplify it? 2 squared is 4 equals just 6x minus 7. Now what? Add the 7. So we get 11 equals 6x. So then x equals 11 over 6. Yep. Now, remember that you should always plug it in to see if it works, right? So if we plug 11 6 in, 6 times 11 6, well the 6's cancel, right? So you have 11 minus 7. That's positive. That's what we care about, right? So that's enough to check. Okay? So then, the next one is, we have log base 2 of x plus 9 is plus log base 2 of x plus 11 is equal to 3. In front of you that just came in, there's little cupcakes up here if you want one. So, what should we do with this one? Any ideas? What don't we like? It's always a good thing to think about when you're trying to solve an equation. The logs. We really don't like that there's 2 separate ones and that the other side isn't a log, right? It's just bad combination for what we've done so far. So what could we do with these two logs? Not cancel them, but combine so that next we can cancel them. Because you can't cancel when it's separated by plus or minus. Okay? So you have to make it into one term. So plus in the middle means we do what? Multiply what? The insides. Yep. So we have log base 2 of x plus 9 times x plus 11 equals 3. That side didn't change. Now we could do both methods, right? Either just go straight into converting it into exponential or use the inverse method to cancel. So which method do we want to use? Just the conversion, right? It's less steps. So 2 to the power of 3 equals this stuff, right? So let's go ahead and FOIL it out, right? So we have x squared plus 11x plus 9x plus 99. Ran out of room. So then, let's simplify, combine like terms and so forth. 2 cubed, 8, equals x squared plus 20x plus 99. So then 0 is equal to x squared plus 20x. What plus 91? All right, so now we have to try to factor that. 91 factors into 7 and 13. I can't do it in my head, I just remember because I already did this problem out for my notes. So you just try numbers until you get ones that actually divide, right? So we get 7 and 13, multiply to 91, and because it's plus, and plus here, add to 20, right? So that means 0 is equal to x plus 7 and x plus 13. So then x equals -7 and -13. Are we done? Usually if I ask, it's a good indication that we're not, right? What should we do now? Plug it in. Check them both, right? In the very original. If we plug in -7, -7 plus 9, positive. That's what we care about, right? If it's positive or not, inside the log. -7 plus 11, positive. So the -7 is good. What about -13? -13 plus 9, not positive. That's enough. One spot of it being not positive inside is enough to say no. So to say yes, it has to be non-negative or 0 everywhere. To be a no, it just needs one spot that it doesn't work. Okay? That's 5.3. So we were really, really close to finishing it. 5.4, sorry, 5.4. That was 5.4, right? 5.3. 5.4. I'm just really confused. That's what you were saying earlier. Okay, now I get it. She was trying to tell me 4, and I was very obstinate that it was 3. Okay, so then 5.5 is applications of logs and exponentials. And this is our very last section of material. I mean, it better be because we're close enough to the end, right? So now what we're going to do is have a few setups of exponentials and logs to solve for, and then we'll go into some word problems, okay? So the first one is e to the 3x equals 10. So we want to solve for x. How do we get to that x? natural log because that's the opposite or inverse of the e. So take the natural log of both sides. Now, I do want to just mention this is not the same as 10 ln. You're not multiplying by ln. You're taking ln of something. So the ln has to go first. Okay? So this is bad. Don't do that. Do ln of whatever you're saying it is. Okay? So then what does this simplify down to on this side? Just 3x, because the natural log and the e cancel, so then the 3x drops down. So 3x is equal to the natural log of 10, and then just divide by 3. So then x is equal to the natural log of 10 divided by 3. Now that 3 cannot get to that 10, because it's dividing the natural log of 10. It's like the 10's in a root. You can't get inside of a root, right, through division, so you can't get inside of a log. So we would find out what natural log of 10 is, right, and then divide that by 3 if you needed the decimal. In this case, it's enough to leave it here, okay, in the exact form. All right, so we've already kind of seen, yeah, question?
So in the homework or the test, whatever, it would ask, keep it in the...
If it wants a decimal, it tells you how many places to round to, right? Or if it makes sense in the units. So like if it's money, then they want a decimal because, well, that is money. I have no idea what that is, right? But if we were to solve it, then round to 2 places, and now I know exactly how much money that is or something, okay? So sometimes it just makes sense what they want you to do. Other times they'll tell you for sure, okay? And if they don't, I will totally answer that type of question on a quiz, test, final, whatever. I don't mind answering that because that's just a how do they want the answer question. That's not math to me. That's just putting it into the computer correctly. All right, so we've seen in a couple sections ago some applications of exponentials with the growth decay, right? So we did like population and a few other different kind of real world setups, right? So we label that as a kind of anything that can grow exponentially like that is modeled by that sort of equation. So by that sort of equation, I mean the A equals P e to the RT, okay? There's a few versions of this. This is the one that you see most frequently. The only other kind of version of it is sometimes they call A P of T, and then P P0, and R can sometimes be K, just because they like to change letters. They don't mean anything different, and they're not like, oh, you use this in this case and this in that case, and they can't switch. They mean the same thing, okay? Recognize them both, but just know one of them, okay? Generally, I would probably remember this one because you'll see this one the most often out of them both. So let's remember what all of these different things are. So P is what? Do we remember? The initial amount. Then E is just a constant, right? It's an unknown constant because it keeps going on forever and ever, so you can't ever write it all down, but it's constant, it doesn't change. It's just 2.71, so on and so on. R is the, sometimes it's rate, but it's the growth or decay constant, okay? If it's positive, obviously it's growing. If it's negative, it's decaying, okay? So, it is the growth if it's positive or decay if it's negative. T is your x variable, okay? And in all of these cases, it will be time. Do we remember what A is then? No? So if P is the initial amount, A is going to be the amount at time T, whatever T is. So amount at time T. All right, so there's our kind of model equation that we use for all of these different cases. This is more so used in like science and such. So those of you going into the business section of methods won't necessarily see this as much. You'll see a few cases here and there, because you can use it in interest rate equations, but it's more used in like bacteria growth or cell cultures and so on like that. All right, so first word problem here is, we're back to the US population in millions is modeled by A equals 310e to the 0.0009, no, 1 too many zeros, just 2 zeros, 00965t, where t is the number of years since the number of years since 2010. All right, so what we first want to do is find out, when does the population reach a certain amount? So in this question, they're asking about 350 million. Okay, now my arm's tired. So, we have the equation already, right? We're just being asked, well, when does it reach a certain amount? So what are we looking for? What variable do we want to solve for? T, because that's the when, right? So when does it reach a certain amount? Well, what is the amount? Where does that go? So where do we plug 350 in? For A. So they gave us the initial already. In 2010, we had 310 million. So now, in what year, kind of thing, when does it reach 350? So that's just plugging in 350. So we have 350 equals 310 e to the 0.00965t. Now, we have to solve for t, and it's in the exponent. It's no different from this. However, we have to get the e by itself first. Okay? So just divide the 310 over, essentially. Okay? So that means, because we're dividing things with zeros on them, they can just cancel each other out. So we have 35 over 31 equals e to the 0.00965t. So now that we have the e on its own, what can we do to it? Take the ln of both sides. So, natural log here, make sure that ln is of that fraction, not just one piece. Okay, don't assign it to somebody just because you said so. It's everybody. And then natural log of that side, so that those cancel. And then we have the natural log of 35 over 31 is equal to 0.00965t. So t is just this divided by that decimal, right? no matter the setup kind of thing, whatever numbers you have, it is that same steps that we just did every single time you want to solve for t. Okay? These questions suck because you have to do the same thing over and over again. Okay? And then all the decimal rounding and stuff can make you get it wrong for silly reasons. But it's the same steps every single time. So that part makes it kind of easy. Okay, so at this point now, we know that this is when it reaches 350 million. If we plug that in, and if your calculator is one that it's a one-step kind of thing, you can't enter in a whole equation at once, you have to do 35 divided by 31, enter, get what that equals, take the natural log, get what that equals, and then divide by the decimal, okay? Otherwise, it will go very wrong very quickly, all right? You should get approximately 1258 years. 12.58, sorry. That point went right into that too, so. But I'm like, that is way too big to only grow 40 million. Yeah, way too many years. Okay, so that means what year is this? $2022 and change. Yeah. All right. So next is actually the business version of these equations. If money is compounded continuously, okay? Now that is very specific, compounded continuously, okay? If it's not continuously, it's a different formula. Only when it's continuously compounded do you use the E version, okay? So, with that, we have the same setup, except that we just label all the different things a little differently, okay? So instead of P being the initial amount, it's still the initial amount, we just call it the principal instead, okay? So if it's talking about money, then this is the principal. The money that you had initially before you invested it, okay? Then the A is the amount you get out of the investment after T years. So they literally mean the same thing, it's just we call it a different name when we're talking about it with money, okay? Same stuff either way though. And then R, instead of growth decay, it's now interest rate. Now the one thing, if they give you the interest rate in percentage format, remember to put it into decimal format. So just move the decimal over twice, make it smaller, right? Okay, so if $1,000 is invested at 4%, interest compounded continuously, yeah, I think that's right. It's way too many O's and U's and all over the place. How long until you double your money? And this is applicable, right? So if we put money into an account, we want to know how long it would take before we have a certain amount in there, right? Especially if you're saving up for something. So, same equation set up, right? So we have A and P and E is its own thing, R and T. Those are things that we could be given or could be told to find, right? Those 4 things. So what were we given? P, because we're told initially we have $1,000 to invest. So we have $1,000 here, and it's invested at 4%. So what's that? That's R, and it's 0.04. I always write the 0 in front just so I don't lose my decimal, because I have. I mean, obviously I lost on this one, so even stuff in front can't help you all the time. But if you have multiple zeros in front, something funky's going on, right? Some decimal should be there somewhere. Okay, now what? What else did they tell us? They told us A, because they want to know how long, so that's, right, what they want to know, how long until you double your money. Well, if we start with 1,000, then that means we want to end up with 2,000. I mean, we could go for more, but that's what they want to know for this question. So let's set it up. We have 2,000 equals 1,000 e to the 0.04 t. Same setup every time. And this is the exact same calculation we were doing that time, right? It just repeats itself over and over again. So, always get e by itself first, right? So divide by 1,000. If I divide 2,000 by 1,000, what am I going to get? 2. 2 equals e to the 0.04 t. Now I want to point something out, so much so I'm going to use a different color. If you double, okay, that failed. If you double, there we go, it will always equal that number. So if we wanted to triple our money, it would end up equaling 3. Quadruple, 4. And I don't know how to say the other ones. Quintuple and so on, okay? So you can go straight here. That's fine, okay? And just say it equals the amount that you want to get, okay? So from here, what do we do? Take the natural log. So the ln and e cancel. Natural log of 2 equals 0.04t. So then t is equal to natural log of 2 over 0.04. If we plug that in, we get approximately 17.32 years. Sorry?
Dividing the 4 over.
Yes, the 0.04 over. And then I just wrote t equals instead of equals t. I don't know, I've always done it that way, so it just happens kind of at this point. I don't know, I've programmed my brain enough that it's hard to not do it. Okay, so now we have similar problem. Yeah, I can do it. So we want to know what is the interest rate necessary for an investment to quadruple so that's times 4, right? After 10 years of continuous compounded interest. I'm going to do it CCI, continuous compounded interest, because I'm just tired of writing and trying to figure out the O's and the U's and so on. Okay? CI, continuing, oh, the whole thing? What is the interest rate necessary for an investment to quadruple after 10 years of continuously compounded interest? So, in these kind of cases, right, let's figure out again what we were given and what we want to find. So we have our four things. We have A, P, R, and T. So were we given A and P? In a roundabout way. Because they told us we want to quadruple. So we have to use this theory here. A is 4, P is 1. So you start with 1, you quadruple it, you get 4. Go with the simplest version. Technically, you could choose whatever you want and just times it by 4, but why not just choose 1, right? You just can't use 0, because obviously if we quadruple it, it didn't change. And that is a very, very boring and very bad investment, right? We did nothing, we got nothing. Well, not a surprise, but not a great one either. So, what about R? That's what we want to find. What about T? After 10 years. So we're basically saying we want to quadruple. We can only put money in for 10 years, right? What rate do I have to be able to get from the bank to do this? Okay? So if I get a better rate than this, then it's going to take less than 10 years to quadruple, or it'll more than quadruple in 10 years, right? But if it's worse than that, it won't quadruple in 10 years.
Can you restate that?
Restate it? Okay. So what we're going to find is the ideal rate, interest rate that we want from the bank. If we get something lower than that, it's not going to reach
Lower than what?
whatever we find R to be. So say it's 0.5. That's 50% interest. 0.05, that's more realistic. So if we find 5% is our answer. So if the bank only has 3%, we won't get quadruple our money in 10 years. But if the bank gives us 6%, well then we will quadruple in less than 10 years or get more than quadruple in 10 years. Does that make sense? Yeah. Okay. So it's basically, this is like what we at least want, more or less, or want to get close to. So let's set up our equation then. We get 4 equals, it's a 1, so you can write it if you want, but you don't need to, because it's just 1, right? E to the, we don't know R, but we do know 10, so 10 R, we do know T is 10. So, we already have E on its own. We can just go right into taking the natural log of both sides. And then natural log of 4 is equal to 10R. So then R is equal to the natural log of 4 all divided by 10, which is approximately 0.138 or 13.8%, right? Now be careful on this because a lot of times they will want the percentage, okay? So if you give them the decimal, it will mark it wrong and you just did all that for nothing, kind of. Okay, so just don't forget that last important step. Okay, so now we're going to talk about the population of lionfish. Slightly, works for us. So we have population of lionfish. In an Atlantic sanctuary. Started growing exponentially. from 10 to 2,600 in 4 years. Or worse than rabbits. 2011 through 2015. So, we're assuming uninhibited exponential growth. What that means, it sticks to the pattern of the equation. Okay, there's no like, they went in and took 10 out in the middle or something. They just, there was 10, they left them alone. They did their thing. Okay, so we want to know, what will the population be in an additional, that's an important thing, additional 5 years. Okay, let's decipher all the stuff that I just wrote down, because that's a lot. When we have these types of equations, where the question is set up like this, that you are asked about, you know the initial, you know what it went to, you know years, you don't know the rate, and then you're asked, well, what is it in an additional time frame? It's the easiest to set up kind of like a chart kind of thing. Literally, it's just this. So, t equals 0 times 0, in this case, 2011, okay? It does not hurt to label. Is the initial of 10, right? This is a way to sort your information out, and you see exactly what you have and what you don't have. The next piece is A, when t is equal to 4, right? So in 2015, it was 2,600. I always put R here. We do not know it. However, we want to ultimately know this. When t is equal to what? 9, because it's, oh shoot. When it's an additional 5 years from the beginning, right? From the 4. So, total of 9, and that would be 2020. So, to get to this and find it, we need R. That's why they gave us this middle point, so that we can set up an equation first, find R, then use it to find A. Alright, it's multi-step. But the last step is just setting up the equation and plugging it in the calculator. So that gets real simple once we actually find R. So let's set it up. We have 2,600 is equal to P, which is 10, E to the RT, don't ever use this T because that's just for P. Your A has to match your T. Okay? So that means we have 4R. Alright, so now get E on its own. So divide by 10. So we have 260 equals E to the 4R. And then we can take the natural log. These cancel. So we have the natural log of 260, I almost did it again, equals 4R. That's a terrible R. So then our R is the natural log of 260 over 4. But we're not done, because that's not our ultimate question that we were asked. We have to set up the equation one more time with this R in it. So what that means, we do not know A. Don't use this one, that's the middle point A, just to find R. So A is equal to, still use P. P is always the same when it's the same question. E to the R times T, so times 9. I'm going to put the 9 in front just so that it doesn't get sucked into the ln. ln of 260 over 4. All right, how you put that in the calculator? 260, take the ln, multiply by 9, divide by 4, right? You see how we're working our way out the exponent? And then put it in the e, in the exponent of e. There should be a specific button for the exponential e and not just e, okay? And then multiply by 10. If you have one of the calculators that it's one step at a time, okay? So start inside the ln and work your way out and down, down and over, okay? So, lot to type in. If you type it in all at once, make sure to parenthesize this whole thing and what's inside the ln, okay? So there should be 2 sets of parentheses at least in the exponent. I'm sorry? Just make sure not to use a rounded version of it because it will give you the wrong answer then. So if you keep it in your calculator and then just use it within the next calculation, totally, go for it. But don't write it down and then use that approximation. Because they usually sometimes will pick numbers in such a way that it will round wrong if you do that. Because they just are like that. So we should get approximately 2,714,501. Don't use the commas when you're typing it in either, because then it'll think it's separate numbers possibly. I don't know. Sometimes it does, sometimes it doesn't. So just don't on principle. Okay? All right. We have one more of those. And then that's it. All right. So, the concentration of an IV drug decays exponentially if immediately after the drug is right after the drug's put in, there are 5 milligrams per milliliter in the body. And 10 hours later, it drops to 1.5 milligrams per milliliter. It's the question that never ends. What will the concentration be 3 hours later? It really needs the gym. Just on the board for a minute straight like that. Whew. Yes? In the body. Milligrams per milliliter. It's just the unit. Yeah. So, all that basically really, we just want the numbers, essentially, right? So same setup. P, T, the ceiling, T equals A equals R equals A equals T equals. So what do we have? So right away, we have 5 milligrams per milliliter. So that's our P, and T is 0. And then 10 hours later, we have 1.5. What will be the concentration 3 hours later? So an additional 3 hours later, right? Even if they don't say an additional, they mean because it's continued from that 10 hours, 3 hours after that, so at 13 hours, what do we have? Right? So we have to find R again first to find A. Okay, so how do we set it up? What? Oh, thank you. Okay, so how do we set it up? 1.5, because that's the middle point A, equals 5 e to the, well, we can leave it as just R. It'll negatize itself. Yeah, so because it's decaying, right? The amount of drug in your body is dropping. That's why it has to be re-administered. So I would just always leave your kind of formula as positive, and then when it solves out, it'll turn negative. Okay, it'll tell you it should be a negative. Then you just don't have to remember. It's good to recognize that it should be a negative answer for R, not for A, just for R. But, so then 10R, so then divide by 5. E to the 10R, take the natural log, the whole thing. Then this cancels. We have the natural log of 0.3 equals 10R. So then R is equal to the natural log of 0.3 over 10. I just simplified that. And so that's our R. And then we can set it up in the final equation. So that A is equal to 5e to the, what's the new t? 13 natural log of 0.3 over 10. And we can plug that in and get approximately 1.045. Okay. Sorry, I ran through that quick because we're technically at past time. And I just wanted to finish, and that's it. That's our last lecture. Truly, last lecture. So we'll